everyone for joining us today for this webinar on PCI Express Gen 6. We'll be looking at what is the future measurement methodologies for this new data rate. We'll be focused on TX and RX today, and really those kind of key new challenging measurements that we see coming as the specs mature, and talk about what we know today, what challenges are still present that need to be addressed, and kind of where we see things going. All right, so we'll go ahead and jump right into the content. And here's the agenda that we have for today. So we'll start with specification updates, right? This is always an indicator of maturity of this new generation. So we'll take a peek at that. Then we'll jump into Gen 6 base TX measurements. So we'll focus on the transmitter. We'll take a look at SNDR has been a focus as it's a new measurement for Gen 6. We'll look at uncorrelated jitter and discuss some of the other measurements that we see being added or updated for this new PAM4 signaling for 64 gigatransfers per second. Then we'll look at receiver testing, right? So definitely a challenging aspect of characterizing either your SerDes on the physical layer or at a system level as well. A lot of the work that's gone on so far has been focused on base spec level or chip level verification and testing. So we'll have a slight lean in that direction today, but also talk a little bit about what's coming as we see more maturity developing on the system level standards as well. And then for the last topic today, we'll look at solutions from Tektronix, right? So what do we have today? What do we see coming this year, next year, et cetera, and give some options for how to best engage with Tektronix to do some of that early setup and verification of your test chips. All right, so for the first agenda item, we will look at the PCI Express 6.0 specification updates. Let's start with PCI Express evolution, a little bit of background, timing of these different generations, how we've gotten to all the way up to PCI Express Gen 6. So the table in the upper right shows the progression from Gen 1 up to Gen 6. And first we've got our bit rate per lane, right? So this is really the raw bits that are transferred across the channel. And you can see we've gone from 2.5 to 5 to 8 to 16, 32, and 64, right? 64 is where we're at for Gen 6. This is the first time we've introduced that multi-level PAM4 signaling. And then you can see the link bandwidth, right? And this then takes into account bits that are lost due to let's say 8B, 10B encoding for Gen 1 and Gen 2. We've moved to 128, 130 for the higher rates, and we're at a 1B, 1B encoding for Gen 6. Next column, we've got lane bandwidth, right? So this is really, now we're talking about bytes across a single lane. And then final column is by 16, assuming you have 16 lanes, bidirectional traffic, how many bytes per second are we seeing? And you can see we started at 8 gigabytes per second for Gen 1, and now we've gotten up to 256 gigabytes per second bidirectionally for Gen 6. So, quite a gain as we've seen this technology mature. And, on average, what we see is the I/O bandwidth doubles every 3 years, and that's what this plot shows here, right? And you can see we have had a bit of a kind of speeding up in the timeline, right? So it took quite a while to get from Gen 3 to Gen 4. Gen 4 to Gen 5 was, roughly a 2-year cycle, and we're seeing that similar cadence for Gen 6. And already some early discussions happening around Gen 7. So, definitely healthy adoption of this technology. We're seeing PCI Express be utilized, not just with the kind of, main KEM connector form factor that we've seen such a proliferation, but also seeing other form factors, M.2, U.2, U.3, OCP NIC 3.0. In addition to that, also seeing, other protocols that are, leveraging what has been done for PCI Express and expanding that to, other applications such as Compute Express Link, seeing a lot of interest and activity there, more of shared memory resources and advanced capabilities to really handle the data-heavy applications we're seeing in the data center. Right. So this is where we're seeing a lot of the interest, adoption, expansion of this technology. For Gen 5, we had a big push for 400G Ethernet host bus adapters at 50 gigabytes per second minimum, cloud AI and modeling, using co-processing, NAND-based storage, and then Gen 6 we're seeing as we're expecting it to debut in 2021. Around the time of 5G critical mass and some of the other points listed there as well. So definitely an exciting time for PCI Express, and this is what we have in terms of the specification snapshot, right? So this is very recently updated. We have reached a really exciting milestone for the PCI Express Gen 6 base spec. So we have got the Rev 0.9 workgroup approval, right? And that level of maturity represents a point where we don't expect a lot of or really any big technical changes to come, right? So it is a very mature spec, and as a reminder, the base spec is the chip level document, right? So it describes on all levels of the stack how that chip will behave. So it's the first spec that we see, and then from there we start to see system level form factor specific specifications come out. KEM is always the first, or it has been historically, and we are seeing a tighter coupling with this spec, also with test specs following that base spec. So that KEM spec is being developed at a Rev 0.5 level, looking at system level, add-in card level, and then once we want to start looking into the specific details of what are the really step-by-step procedures for doing the physical layer testing, that's when we move to the physical layer test spec, also being developed at Rev 0.5, and this is where we're going to get detailed descriptions for transmit, receive, link equalization, TX link equalization, PLL bandwidth, ref clock testing, right? So as I mentioned, tighter coupling, those are maturing quickly as well. Okay, so let's look at some of the electrical changes that we've seen progressing from PCI Express Gen 4 to Gen 5, and then currently the direction we're moving to Gen 6. And I put everything Gen 6 as TBD, right? This is not a fully released specification, so this is a indication of what we expect, but as I mentioned, we've reached a pretty high maturity level. So data rate has gone from 16 gig to 32 to 64 gigabit transfers per second. In terms of our loss budget, the add-in card loss budget is a good indicator of how this will be mapped out. All right, so add-in cards for Gen 4, you could have 8 dB at 8 gigahertz. Gen 5 that went to 9.5, and now 8.5 at the 16 gigahertz Nyquist for Gen 6, right? So that's a very clearly defined budget for the add-in cards, and any additional is kind of left for the system to utilize, right? It's not explicitly defined. It is somewhat implied by what's the total channel loss that we use when we're testing receivers, right? And we have introduced a range there because we actually use that loss as a knob when calibrating our stress die signal for receiver testing, right? So for Gen 4, that was a 27 to 30, 34 to 37 at Gen 5, and 30 to 33 at Gen 6, at the respective Nyquists, right? So that's kind of how you get at that loss budget question and how that's defined. Starting to see more advanced capabilities in the receiver equalization. So the two main blocks that we see there are CTLE, the continuous time linear equalization, and DFE. So for CTLE, we've gone from 2 poles and 1 0 to 4 poles and 2 zeros, and now we're up to 6 poles and 3 zeros for Gen 6. And DC range 5 to 15 dB, and 1 dB step sizes. We'll talk about that a little bit further on another slide. And DFE, we're seeing advanced capabilities being added in terms of additional taps. So we've gone from 2 to 3 to 16. We'll also look a little bit more, delve into some more details on DFE too. Eye width and eye height, this is looking at what is that target eye width and eye height that you use when you're calibrating your stress die. And I'll note these are at E⁻12 for Gen 4, Gen 5, and Gen 6 is now at E⁻6. So we've introduced a light version of forward error correction, and we test our receiver to BER of E⁻6. So now we're at an eye width of 3.125 and eye height of 6 millivolts. So and that is at the top eye, since we're now dealing with 3 eye diagrams for PAM4. And part of this talk will be stress die calibration and receiver testing as well. Seeing an overall tightening of the ref clock jitter limits. This is one of the ways we've been able to achieve these line rates that we're at. So we've gone from rough clocks that had to have jitter after filtering has been applied below 500 femtoseconds, then to 150, and then under 100 femtoseconds. So that definitely represents a new challenge. Is how do you do a measurement at less than 100 femtoseconds? We've seen a lot of advanced capabilities come up there for Gen 5, and we expect that to continue for Gen 6 as well. Scope minimum bandwidth, we've gone from 25 to 50, and we've stayed at 50 for Gen 6 as well. All right, so we'll jump into 64 gigatransfer per second, so Gen 6 base transmit measurements. So we have had a change in the behavioral definition of the transmitter equalization in the spec. So what we've done is we've added a second precursor, right? So previously we've had one precursor, one postcursor, and of course the main cursor. So you can see in the diagram in the top left that second precursor has been added. And one thing that's exciting and I think a little bit overdue, I'm glad we're looking into this now, is there's a set of presets. So these are predefined coefficient settings that are commonly used. That's the intent. And they were defined as P0 through P10, preset 0 through preset 10 for the previous data rates. down to Gen 3 at least. And now we're defining them as Q. So Q0 to Q10 to distinguish, because what we've done is we've, first of all, there's the second precursor, right? So we had to account for that. On top of that, we've tried to make these more useful, more appropriate for the channels we expect to see, right? So we're seeing heavier precursor weighting, right? So you're seeing less post-cursor than you had with the previous presets, larger coefficient values for the first precursor and some given to the second precursor as well. And that's based on, extensive, full channel simulation work that's been done. So those are expected to be, much more appropriate for the range of channels that we'd see for Gen 6. And then also we have numerous optimal presets for RX calibration. Right, so this is great, right? This means, one of the very common tests that many validation engineers will be performing will be able to utilize multiple presets, right, and get very close, which will address different PPGs that are used for calibrating the stress die, variations in test fixtures, variations in replica channels that model kind of the breakout of your test platforms for silicon level testing, et cetera. Also, a new measurement methodology was introduced starting in the Gen 5 timeframe. It is commonly referred to as the AC method. I also hear it called the step response based method. And it's believed to address some of the gaps with the previous VB method, where we were just looking at ratios of a low frequency type portion of the waveform. So now what we're doing is we're taking a step response from the compliance pattern. We take one that's equalized and one that's not equalized. So non-equalized will represent Q0 without any precursor or precursors or post-cursor. And then the equalized will be the preset or Q value under test or coefficient combination that you want to measure, right? And then what you do is you take the non-equalized step and you actually apply cursors to that, and you're trying to get it to match up to that equalized step. And the cursor values that get you to that point where you have a minimized mean square error, those are your cursor values that are then reported, right? So this is a new and approved approach, and like I said, introduced for Gen 5, but required for Gen 6 as well. Okay, so this is a full list of the expected Gen 6 base TX measurements. And what I've done is I've highlighted in green the ones that we're going to focus on today, right? And we expect to do future discussions on some of these other measurements, but there's been a certain amount of de-risking that's happened, and that's internally within Tektronix. We've done a lot of work in this area, and other member companies within the PCIe SIG have been looking into these. So these are the ones we'll focus on today. So that's SNDR, the signal to noise distortion ratio, uncorrelated jitter, and definitions include total jitter, deterministic jitter, dual Dirac, random jitter, and then we've got the pulse width jitter as well, TJ, DJ, DD, and RJ. In pulse width jitter, don't have additional slides on, but I wanted to emphasize this one a bit. It is a challenging measurement, and so I'll speak to it on this slide. And what this really is it's trying to capture the compression of single pulses, right? Because those are really challenging, really challenging for receivers to handle, right? So you can think of it as a really a compression, from one side or both sides. It gives you a very narrow pulse, right? And you could think of this as maybe you have a single or small amount of transitions. Let's say maybe one pulse kind of wedged in between two lower frequency regions, right? So that usually results in a very compressed pulse. And so PCI Express is unique in that it has this measurement. It accounts for even odd jitter, so that's it is inclusive of the even odd jitter, but it is a unique definition to PCI Express, and one that we think requires some attention. For Gen 5, we moved from using a compliance pattern, which was PRBS 23-like, to using a 1010 pattern. And this was an improvement for this measurement. It allowed us to really use the full A to D on the scope, since you didn't have these low frequency sections of the pattern, forcing you to use a non-optimal A to D setting on the real-time scope. So that's persisted, right? So for Gen 6, we're still using a signal that looks like NRZ, right? We call it a low-high toggle signal. And now instead of going from 0 to 1, you're going from 0 to 3. So it's a 0-3-0-3 pattern. And beyond that, the measurement looks very similar, with the addition of we're now allowing compensation for scope noise. All right, so now we'll get into the TX measurements that were highlighted. We'll start with SNVR. Right, so this is a topic of interest for many people. A lot of time was spent on this within the PCI SIG, and I'm sure there'll be more work done on improving the measurement methodologies as we progress to 1.0 specification and beyond for that base spec. So signal to noise distortion ratio. The equation is shown here. So it's a ratio of the P max. So this is the peak of the linear fit pulse. So we're following an IEEE definition for establishing a pulse response from a data pattern. And there haven't been any major changes to that methodology that was adopted from IEEE. So we establish a peak, a linear fit pulse, or we establish a linear fit pulse, and then we find the peak. And in the denominator, then we're looking at two values: standard deviation of an error waveform, sigma E, and standard deviation of noise. All these terms are squared, and then we take the log of that value. P max is fairly straightforward. Sigma E and sigma N require some additional discussion. So I've got two slides on each of those. We'll start next with sigma E. So I mentioned we were able to establish a pulse response with this linear fit approach. Once we have that, we can take that in hand with the concept of superposition. And what we can do is we can reconstruct, one occurrence of the pattern, right? And, the linear fit pulse, another interesting comment on it is it kind of approximates the, RX equalization reach, right? Because you can think of it as, however long you let that tail of the pulse response be, that's can map to the number of taps in your DFE, right? At least that's the way it's been viewed within the IEEE sphere. And we've taken a slightly different approach for PCIe, whereas we're allowing that tail to be, extremely long. So, we're really looking more at what is the best possible SNDR, given the signal, and not factoring in that limitation in the same way of the RX equalizer, specifically DFE. Okay, so once we have that reconstructed waveform that we've made from the linear fit pulse, we can take the difference of that waveform with an averaged waveform from our original capture, right? And that becomes our error waveform. So you can think of this as, you're really looking at, okay, we have the pulse response of the transmitter. We're reconstructing the waveform with that. We're comparing it with the actual waveform we captured, averaging out, kind of noise, et cetera, there. What's left is this error waveform. You can see that in the bottom image here. And, this is really the non-compensable aspects of the signaling, non-linearities, limitations in the RX equalization, although we've tried to kind of minimize that with the approach for PCIe. And then the RMS of this waveform becomes sigma E, right? So this is kind of a novel aspect of SNDR is, we're creating a new bucket, and we're putting some non-compensable aspects in there that were, been ignored in earlier signal to noise types of analysis. So pretty powerful aspect of SNDR. Next, we'll look at sigma N. So you can really think of sigma N as the noise, right? This is the noise that you have on the waveform, and we have some advanced techniques that we've introduced to best characterize that. But it's taken from the original waveform. This is a real-time capture. And for NRSD, historically, what was done is you look for low slope portion of the waveform. You want that low slope portion because you don't want to be translating your noise. You really want to just look at the voltage noise independently and not be looking at the jitter for this piece, right? For PAM4, similar. So for now, we have to consider 4 levels, right? And so we find these noise values, 4 levels, and then we take the mean of these RMS values. And I'll get into a little bit more detail on the unique approach we're taking for PCIe. So this is looking at more PCIe Gen 6 specific SNDR. How do we expect this to be defined? So for the pattern, we have this new Gen 6 compliance pattern. It does have these low frequency sections of the waveform at all levels. We've got a long run length of 0s, 1s, 2s, and 3s for all 4 PAM4 levels. SSC does need to be considered in this measurement, especially for designs that will be supporting SRIS. SRIS is when you have separate reference clocks between the 2 link partners, and both have implemented their own SSC, which is not exactly correlating between the 2. For this measurement, we set TX equalization to 0, Q0, so the precursors and the postcursor are set to 0. The real-time scope capture, we're using a scope bandwidth of 50 gigahertz, record length, minimum of 250 repeats of the pattern, and filtering a 4th order BT filter with 3 dB roll-off from DC at 33 gigahertz. All right, so this is following some filtering methodologies that we saw in IEEE, but setting the 3 dB point appropriately for this technology. Sigma E, we talked about that a little bit. So this pulse length, this is really the part that we've extended much further. So this is that tail of the pulse. So we're taking out 600 UI, right? So this is a big deviation then from what we've seen in IEEE. Pulse delay for this is kind of the information you get before that pulse, and we're requiring 32 points per UI, which can and most likely will involve resampling to get you to 32 points per UI. And just focusing on the PRBS portion of the compliance pattern for sigma E, so not inclusive of those low frequency sections. The clock recovery that gets applied is not explicitly called out, so it's really DSP implementation specific. And then for sigma N, I mentioned some more techniques that have been developed. So we've identified the flattest portion of those long run links. So looking at the 61st UI out of those 64 run links. And then within that UI, we're looking at 8 evenly spaced points. And then taking the average of those, and we do that across all levels, and then average all of those results to get what we believe is a highly accurate sigma N. Okay, so a lot of background on SNDR. It is a fairly complicated measurement, new to PCI Express. I wanted to spend a little bit of time there. But now let's look at some data, right? So this is a feasibility study that we did, and we wanted to look at the more challenging aspects of this measurement. And those are supporting this measurement with a channel loss, which we expect for base silicon testing could be as high as up to 15 dB. Also being able to do this test with a new pattern, which creates challenges for clock recovery because you have these long run links, and compound that with a additional challenge of SSC, the spread spectrum clocking. Right. So when you put all those together, you've got a worst case that is challenging and in ways that you haven't seen for that IEEE measurement. So wanted to de-risk this. So looking at the data, we're starting on the left with a 1.5 dB channel. It's cable only, and going up to 14.3, almost 15 dB. Right. Our signal is generated by here the Enritsu BERT. So this is a 32 gigabaud PAM4 source sent through that channel, and then captured on the Tektronix 70 gigahertz scope. Of course, our bandwidth is set down to 50 gigahertz. For each channel, we looked at SSC on and SSC off, both cases. Scope bandwidth here, this is the BT filter, not the scope bandwidth was 50, but we're setting that BT filter at 33 using the Gen6 compliance pattern, that NP value of 600. And we are looking at scope noise removal as well, so that is supported for this SNDR value. And the good news here is we've seen pretty consistent results, definitely consistent from the SSC off to the SSC on case. You can see our kind of highest values are in the range of 40.7 dB, and pretty stable up to that 15 dB channel as well, right? So we do have a slight reduction to 39 dB, and probably still a little bit of room for improvement, but definitely it shows it's feasible. We're passing that spec limit, and getting healthy SNDR values. So next, I want to look at kind of the second area of focus that we've seen within the PCI SIG, and this is the Gen6 uncorrelated jitter measurements. And I'm going to jump right into the requirements and what we have today, and then we'll look at a couple sets of data that we've explored as well. So early on, we were looking at something more similar to what IEEE has done. We were looking at a J6U, JRMS. Eventually, we moved back to kind of the historical approach using uncorrelated jitter for PCI Express Gen 6, right? So at a high level, the definitions are pretty similar. How we get to those measurements are a little bit different, right? So, first of all, we've got, multi-level signal to deal with now. Second of all, we have, a very high sensitivity to noise. Since we have those 4 levels, smaller eyes to begin with. So, scope noise or instrument noise needs to be compensated for. And, a generic approach where you compensate the same way, for all parts of the pattern was shown to be, unrealistic and not accurate enough for the spec limits that we've seen. So we have this 52 UI jitter measurement pattern. And it has 4 instances of all 12. So there's 12 possible transitions for PAM4, right? If you think about it, 0 to 1, 0 to 2, 0 to 3, you can kind of work through that, and you get 12 combinations, so 12 edge types, right? There's a couple extra bits in there for DC balancing, but essentially you have 4 instances of every type of transition, and each one will have a slightly different impact from the neighboring bits in terms of the ISI, right? And so what we do with the noise compensation is we look at each individual transition or edge, right? And so we're looking at given the slope of that edge, what is the appropriate amount of vertical noise that will get translated to jitter, and then let's remove that accurate amount for that edge, right? So that's the approach that's been done. And so essentially we're determining jitter on each individual edge. Once we get those results, then we come and take those results across all the edges, average the results together, and that's what we check for pass-fail in the spec. But it still allows us to do that more improved method of noise compensation, right? So a lot of work has gone on here, and definitely feel like we've gone in a good direction, and data that's been presented publicly is encouraging and supports that as well. In terms of the real-time scope, so 50 gigahertz bandwidth as well, record length of 2 million UI, and that gives us 37.5K, I think we're missing a K here, UI per unique edge, right? And one question that naturally arises is, is that sufficient, given for each edge to get a result that would match if you had 2 million of each transition, but that would require a much longer capture or more complicated approach. So we have some data looking at that here in a moment. In terms of filtering, 4th order BT filter, so same filter, 3 dB roll off at 33 gigahertz. We've talked about it being measured on all 48 edges. You do have the ability to, use a CTLE, whatever gives you the lowest RJ, essentially uncorrelated RJ, right? So it's either the no CTLE case or one of the 15 CTLE curves that's currently defined. There's been a discussion about, maybe we also change the granularity of the CTLE family. Maybe we go from 1 dB step sizes to quarter dB. We've seen that in the past for stress die calibration, so I'd say still an open question. And then we've talked about the scope noise compensation. So let's get into some of the data next. All right, so this shows the general setup that was used. So the Enritsu MP1900 BERT, 32 gigabaud PAM4 source connected to the Tektronix scope. Most of the work so far has been with very short channels. I think the next step is let's look up to 15 dB. We've done some internal work on this and expect reasonable results, but we will have more data on that soon. And so, we're capturing the waveforms. We're using the Tektronix PAM4 analysis app to, do this characterization for the DSP tool aspect, which, handles, latest definitions in the spec, does the noise removal, reports the values. This shows some of the data here. This was very early on when we were still focused a little bit on JRMS. I'm going to go ahead and jump to the next slide. I think this one's a little bit more interesting. So this is now the random jitter with the impact of scope noise removal, right? So the light blue curve is, before we've done the compensation for the noise, and the darker blue is after. So you can see the impact. And interestingly, you can also see this trend where the edges that have the sharper edges, let me say, like the transition 0 to 3, 3 to 0, you see the least amount of delta once you've compensated for noise, because you have less conversion of that vertical noise to jitter. But then the flatter edges, let's say 2 to 1, you can see it where you've got a bigger impact because you've got more translation of that vertical noise to jitter. And so the sigma RJ mean came out to 316 femtosecond when you average across all these edges, and 285 femtoseconds with the noise removal. Another thing we wanted to look at was, I mentioned earlier that we only get 38K edges for each transition type. So we wanted to look at the trend across a deeper population and see, does this definition where we've said, okay, we'll do the measurements on individual edges, and then we'll average the results together in the end, does that match with the approach where we had a longer record where we had up to 2 million UI, right? So that's kind of what we were looking at here. So for all transition types with a single capture, so it's a 2 million UI capture, that means we have 38K edges. Our mean came out to 285 femtoseconds. Then with this deeper population, where we actually have 2 million of each edge type, and we were able to build up this population with multiple waveform captures, we came out to 288 femtoseconds. So we were able to show that was matching relatively well, which is great. Good sanity check for the spec. And this is a very similar view, each of the curves looking at different edges. And you can kind of see that, flattening out over time. But, with the same comparison here, now this is total jitter and the impact of the population. With the way we defined it today, TJ, we get 2.85 with a 2 million UI capture. And if we looked across a deeper population, we got 2.92 picoseconds, which is also very closely matching. So this was confidence building for the methodology we defined in the spec. All right, so I want to go ahead and move on, make sure we have plenty of time to talk about RX calibration and JTOL. All right, so some borrowed aspects from Gen 5, some new elements introduced for Gen 6, and want to spend a little bit of time here. There's been pretty extensive work, mostly on the stressed eye calibration methodology so far. Still kind of in the early stages, not a lot of silicon available to do the JTOL, but some early analysis there as well with what's available. I'll focus a little bit more on the stressed eye today. So first I'll point out, I mentioned earlier, we'll talk a little bit more about receiver equalization, how that's changed going to Gen 5. So we've got this more complex, more capable CTLE that does a better job of removing the impact of the channel. 6-pole 3-0 CTLE definition. We've got a range to give us this family of curves of DC gain going from 5 to 15 dB. So, much more capable CTLE. And in terms of DFE, we've also gone up to 16 taps, right? One thing that's nice about DFE is you don't amplify noise, right? So DFE is nonlinear, but you're not amplifying the noise, right? So that's a nice aspect of the DFE, whereas with CTLE, you definitely can't have some of that amplification. So the DFE is up to 16 taps. And you can imagine this diagram at the top right. It was just extend to show all 16 taps. The DFE taps are constrained in a new way, and this is to minimize burst areas. Burst errors. So you can't have this instability with DFE, right? Where you incorrectly identify one bit. And then as a result, you shift following bits in an incorrect direction. And you can kind of have this ripple effect of errors, right? So there's been constraints added to minimize the likelihood of these burst errors. And empirical formulas in the spec for this, just something to be aware of. Stress die calibration is definitely one of the more challenging aspects of receiver testing at 64 gig. Also repeatability. Now we'll have to do validation and compliance testing across 6 data rates. 2 legacy NRZ, 1 PAM4 for receiver testing. Noise from equipment now has to be taken into account in new ways. There's been some spec changes to account for that in the receiver section as well. We've got to deal with jitter tolerance testing, BER RX testing in the presence of SSC. We've seen within Gen5 more of a push to do as much of the testing as possible with SSC turned on, but create some challenges in actually implementing that and getting believable results. Also post-processing tools, right? So, historically SIGTEST has been used. CSIM has been another tool, waveform or a statistical simulation tool that's used for stress die calibration. Those tools have to be updated. Also, for receiver testing, the back channel equalization, right? So this is, you've sent a worst case stress die signal to the receiver under test, and that receiver is in loopback. It digitizes that analog signal and needs to send that information back to the error detector on the bit error rate tester, right? So that back channel, you have to ensure that you don't introduce errors within that channel, right? So, it continues to get more challenging as we, move up in data rate, and you have to have that back channel not introduce errors and have advanced capabilities within the error detector to support that. So in terms of the stressed eye diagram, this looks very similar to what we've had for Gen 4, Gen 5. Now we've gone up to Gen 6. So, everything to the left and that blue rectangle is, typically part of the bit error rate tester, and more specifically the PPG on that bit error rate tester. So we've got a 32 gigabaud PAM4 generator. We've got an ability to add TX equalization, an RJ source, SJ source, ability to couple in noise, both differential and common mode noise. Moving to the right, we've got our physical channel that's used for calibrating the stress eye signal that's representative of what you'd see in a true channel. And then on the right side, you've got the real-time oscilloscope. Shown here is the test equipment. You're capturing either step responses, waveforms, and then you've got a post-processing step where you're applying clock recovery, receiver equalization with those behavioral models we've looked at defined in the spec for CTLE and DFE. And ultimately, you're trying to get to that target I. We focus on the top I for Gen 6, 6 millivolts, 3.125 picoseconds at e to the minus 6. And we have knobs to get there. So we've got channel loss, which is our coarsest knob, and some fine tuning that can be done with RJ and DMI to adjust eye width and eye height a bit further. So we did a feasibility study here as well, and we've been doing some follow-up work recently as well. We'll show some of the earlier data. So we're using the MP1900 as our source, using the Gen 5 base calibration fixtures, which we believe, with the exception of crosstalk, to be appropriate for calibrating the Gen 6 eye, and then the Tektronix real-time scope 70K series. And our final channel that we ended up with this for this feasibility study was 33.1 dB at 16 gigahertz. All right, so that's at the max of the range that's defined. So currently the spec is saying 30 to 33, although TBD, as this is still open. And post-processing, we looked at CSIM 1.0.6 version. And within there, we're applying the CTLE, DFE stressors in terms of random jitter, sinusoidal jitter, and the crosstalk term as well. And let's jump into the data, and I'll break this down. I know it's a little bit busy of a slide, but essentially what we're showing here is the solution space. So this is all with one channel. This is the 33, a little bit more than 33 dB channel. And every vertical black line here is a solution, right? So this shows that there's a healthy solution space. Of course, there's tiebreaker criteria defined, and then top row is looking at eye width, and bottom row is looking at eye height. And every individual plot is a different amount of sinusoidal jitter, and then the x-axis we're sweeping differential mode interference, right? So with this channel, looking across the different ranges of differential mode interference and SJ, we see 9 different solutions, 9 different locations where we close the stress eye, right? And those tiebreaker criteria are highest loss channel, which we're already at, and then beyond that, which one gets you closest to your eye width and your eye height, the nominal values. All right, so next we'll look at jitter tolerance methodology. Like I said, not as much work has happened here, but this is kind of what we expect. So the modified compliance pattern will be used during loopback, not the compliance pattern. So this is a longer pattern. It doesn't have those low frequency sections without SSC on the data signal, right? Because that actually is one of the tones that you sweep when you're doing JTOL, and you can see that on the plot as that vertical line at 33 kilohertz. So the TX equalization coming from the equipment, the test equipment source, the PPG on the BERT, can be optimized for that receiver. Right, so the value that you achieve during your stress eye calibration doesn't have to be used. Right? You can use whatever that specific receiver under test prefers. And we independently sweep the 33 gigahertz tone. You can see that in the plot. The amplitude of that tone is different depending on if you're testing for common clock. You look at 1 nanosecond. For SRIS, you test up to 15 nanoseconds. And the JTOL mask that extends between 400 kilohertz up to 100 megahertz is the range that's usually explored. An additional tone of 210 megahertz will be used if SJ is over 0.5 UI. So I want to spend just a minute or two, and then we'll go into Q&A on Tektronix Gen 6 solution space. Let me go ahead and populate this. Okay, so this is what we're looking at for our solution space, and there's aspects of this that are available today, and then there are aspects that will be rolled out, Q4 of this year, and then some into 2022 as well. And definitely, more of a lag when we're talking about the chem aspects, as that spec we're still working on Rev 0.5. But we have a host of analysis tools, SDLA, which looks at CDR, receiver equalization capabilities, embed, de-embed, DPO jet, which handles some of the measurements needed for Gen 6, and then the area of most focus here is the PAM4 analysis app, and that's kind of shown at the bottom there. And that's where we've really introduced the SNDR, uncorrelated jitter, working on pulse width jitter, additional measurements coming soon. In terms of transmit solution, we're looking to support base, chem, ref clock, similar on the receiver side. As I said, some aspects available today, others still coming. Fully automated solution coming as well, using our Tech Express framework, which we've had around for earlier generations, enhancing that, updating that to support Gen 6. And then development around automation for stress die calibration as well. For Gen 5, Tektronix did build and release some fixtures, and those can be used for early enabling of Gen 6 as well. So we're a little bit short on time, so definitely if there's interest, we're open to early engagements. Contact your local representative, and we can get into supporting you as best we can for Gen 6.
Okay. First question, David, is what scope bandwidth is needed for Gen 6 transmit and receive tests?
Yeah, good question. I touched on it a little bit, but it's a little bit complicated. So let's go into a little bit more detail on that. So the nice thing is that our Nyquist has remained the same, and there's also a desire to keep the bandwidth at a reasonable level to address noise, right? So generally, what we're seeing is a 50 gigahertz scope bandwidth requirement, and this is, we really looked at it for base testing so far, right? So I think that one's pretty well understood. Spec's not officially released, so could change. But I think 50 gigahertz is what we're looking at, and then we're utilizing that BT filter, the fourth order filter, with a bandwidth of 33 gigahertz for 3 dB to do some additional removal of noise.
Okay. Is SIG test going to be used for compliance on Gen 6 with all these new measurements, or is there some other tools that are allowed or used?
Yeah, that's a very good question. I think it's a little bit unknown right now. There hasn't been a roadmap for a PAM4 version of SIG test provided publicly. I would expect that to come, but we don't know when that will be available to members, or broader than that even at this point. CSIM, developed by AMD and provided to the PCI SIG members, is available supporting PAM4 today. So work that we did on stress die calibration used CSIM. And in the absence of a SIG test PAM4 version, what we've done is we've taken it upon ourselves to enhance our own algorithms in SDLA, DPO jet, our PAM4 analysis app to support Gen 6, right? So data that we've shown on SNDR, uncorrelated jitter, like I said, we're working on pulse width jitter, has been done with our internal tools, and we are able to engage with those today.
Okay. A question about your slide 14. Was feasibility testing done with the Tech PAM4 tool or with the SIG test tools?
Yeah, let me go back to slide 14. Oh, okay, so this was on SNDR. So this was done with the Tektronix PAM4 analysis app. Like I said, we would expect that some date in the future there will be a version of SIGTEST that supports this. We just don't know when. So for that reason, we've introduced this measurement, adjusted it to latest definitions within the spec, added that support for scope noise removal, and a feasibility study was done with that tool.
Okay. I guess we have time for one more. The top eye margin of 6 millivolts, is that after equalization settings are optimized?
Yes. So, in the context of stress die calibration, we're trying to achieve end of channel, post equalization, post clock recovery, an eye height of 6 millivolts at even -6, right? And we have certain knobs, channel loss, sinusoidal jitter, differential mode interference. Differential mode interference really maps to crosstalk in a real system. And then we look at using those knobs to adjust, and then looking post equalization for that target of 6 millivolts.